some factors that we don't observe, so we cannot put it in the observable box, but we can suppose that they influence our observable. And this is something which is quite common in psychometrics, not only psychometrics. Psychometrics is, let's say, part of psychology that deals with quantitative analysis of behavioral data or symptoms of disease, etc. So the idea is to find interdependencies between different items of questionnaires asked both to participants or symptoms of disease, etc., where the probability distribution is built not in time as we do for time series, but across different subjects as if they were stochastic realization of the same organism, if you will. And so latent variable, typically latent variable analysis starts from the fact that, for example, you cannot measure depression as a thing, but we make some assumption that some observables, such as fatigue, insomnia, loss of interest, suicidal thoughts, etc., are, let's say, some markers of depression. So depression will be a latent factor that loads on these observables. So the idea is to measure these things and then have an idea of. So from this, network science has entered this field with networks built between observables or between factors or factors and observables. Here the squares are factors and the circles are observables. And this figure from this book called Network Psychometrics. And then you can look at other papers such as this primer on nature methods, and then of course also some critiques. So there are different families of methods: structural diffusion modeling, network modeling, latent network modeling, and residual network modeling, which share some similarities and some differences. And so this is the typical network that you can observe from observables. So usually what they do is to build a partial correlation network, which is then sparsified using some materialization like Lasso. So here you have the positive correlation in blue and the negative in red. And so this is a network analysis on empathy. Empathy cannot be measured, but you have different latent factors such as taking and empathic concerns. Also some things that Madeline this morning talked about when she tried to quantify empathy. So it's a nice network. It's not very, let's say, compelling in the sense that all these items are grouped together as the factors are. Indeed, if we then apply some higher order analysis with the oil formation, we see that the redundant hyperengine, even if it's a mess, looks like a crop circle, is what it is. The redundant hyperengines basically group the variables, so it's basically a sort of dimensionality reduction, speaks to redundancy. On the other hand, there are some synergistic hyperengines which contain items from the different four latent factors pertinent to the construct. Another network can be, another example is a network of post-traumatic stress disorder where you have some behavioral variables, but you also have some covariates like sex, age, etc. And here we see that we only have redundant hyperengines, so we don't have any significant synergies. So this is a way of constructing the network where, let's say, the higher order mechanisms will be the latent factors, and the higher order behaviors are, on the other hand, some interactions that go beyond the mechanism. Indeed, the network, the resulting network, look different. And so this is a sentence from this primer on how to build psychological networks. And this is, on the other hand, what we propose to do using higher order hyperedges sort with all information as defined as a method in which basically we directly look at groups of variables sharing common information. Now, uh, going a bit further, we can look at synergy between hidden factors. So we have the factors, and then we have the different weights on the observed variables that are in. So we assume that the observable are along this line, and there are some hidden factors. Each of those projects on the observable. And the idea is that we can measure the synergy between these hidden factors using, again, the, the O information and the fact that for latent variables that are independent, then the O information is zero. On the other hand, we have synergy. Uh, and we can construct networks taking into account the dependency on hidden factors. And hidden factors are very important in many cases. For example, in fMRI data, uh, one huge hidden factor is the blood around time, the respiration. So fMRI signal cannot exist without blood circulation, cannot exist without respiration, and of course, everyone forgets. Also, not only the top 10 that's apparently something in general, usually say, oh yeah, okay, fMRI is just a small measure of neural activity, something that would not be possible without blood flow. As a matter of fact, if you take some random noise and you just shift it in time, the same time series, according to the blood arrival time in different brain regions, you obtain the resting frequency observed in real time. So even without any neural network. Now, of course, this is a sobering message. It's not that blood flow and neural activity are completely different. Of course, there is a reason if blood flow has this nice cortex which subserves neural function. But on the other hand, we cannot forget that the fMRI signal is made of both. So, if we look at the synergies between latent factor in fMRI data, we see that we have the higher order function networks, such as the frontoparietal and the default mode, which are more synergistic. On the other hand, sensory networks, such as the visual and the sensory motor, are more independent from this latent factor. And then another application on the cancer culture or the HeLa cell to remind that sometimes in science we do bad things and should be. So now, some of you could ask, okay, you're saying that things that basically incriminate redundancy are synergistic between them. It's not like a contradictory things that you have something which is emblematic of redundancy and still you have only synergy between this. But you can make a simple exercise. You take the XOR gate, which is emblematic of synergy, and you can build a meta XOR gate, where the question is, can we solve the XOR gate given the inputs? So the truth table of this is uh, if we cannot solve either of the inputs, then we cannot. But also, if we can solve only one of the inputs, we cannot solve the gate, and only when we can solve both inputs, we can solve the gate. So this beta table corresponds to a logical AND. So the meta XOR has become an AND, which from the point of view of information and supplies is much less redundant. It's not redundant at all from the point of view of information and supplies. It is still a bit synergistic in the terms of function. And so we have turned one thing into the other. Or if we take copy gate, which is on the other hand emblematic of redundancy, and we make a meta copy gate in which we ask if we know only one of these or two, the truth table of this is an XOR. So we had the emblematic gate for redundancy, which turns into the emblematic gate of synergy if we ask questions about it. And indeed, in a very old paper in 2012, where we tried one of the first non-parsimonious expansions of the transfer entity to find redundancy and synergy. By the way, I just realized that you call this moment like the ultimate. It's too late to write that. But anyway, it's good that at least it means the same thing. I didn't realize up to now. So this thing that we call omega, which is the expansion terms in a Taylor-like series of the transfer entity, again goes up and down to synergistic and redundant variable if we add additional variable in a very simple chain-like system. So yeah, this is curious. Maybe we're not asking these questions, we're just wasting 5 minutes of my time. Now, we heard this morning about Granada Seminar, and of course Granada Seminar can also be seen in terms of conditional probabilities and information condition on the past values of the target. So part of this topic is also the so again, we go back to some efforts of expanding the transfer entropy. So not only taking into account the zero lag interaction, but also lag interaction, which take into account the history of the system. And so this is our first attempt dated in 2012 with this Taylor-like expansion, which worked, not parsimonious. On the other hand, by introducing conditional variable on the definition of all information and straightforward have a version, a dynamic version of the all information which has been used in several papers, including the one by Robin et al., which I discussed at the beginning about higher order signature, behavioral signature of higher order magnitude. Here, on the other hand, we apply to some spiking methods in the decision-making task where we had the three classes in neuron, age, N, and L, which had, let's say, decreasing mutual information between the neural activity and the outcome. So the class H neurons are very informative about the final choice of the animal, and so and so, and L. So we see that for redundancy, even at all size of multiples up to 10 neurons, the amount of redundancy stays the same. On the other hand, the synergy starts very high for the class H neurons and then drops. On the other hand, starts very low for L and then neurons, but then goes up and becomes much more synergistic when we start considering a higher number of neurons. So let's say that even if the individual mutual information between neurons and outcome is very low, then we still have synergy when add more neurons to our model. Another expansion is the local extension of the all information. So if we remove the sum, if you want, either the integral or the sum from the entropy, you obtain the local entropy. So it is basically the contribution point by point to the overall entropy. And indeed, for example, this is a very simple example of a logistic map in which y influences x. But if we look at the local measure, this is the local Granada causality, we see that there are some values that are indeed uninformative for the model. So overall, y influences x. But there are some data points for which knowing the driver makes your model of the target worse. So it's misinformed. And the same can be applied to all information. For example, here is over cellular trial, and we can see that we have some points in which we have redundancies, in which we have synergy. The red dot is significant across several permutations of the points which are completely unimportant. And so this we can see the application of this to the case of a frustrated physics system in which, depending on the sign of this complement J of the probability distribution, we can have, let's say, frustration when the J is negative, and on the other hand, ferromagnetic behavior when J is positive. And so the global O information is basically synergistic in the frustrated case and redundant in the ferromagnetic. If, on the other hand, we look at the local O information, this which is lowercase omega, we see that indeed we have, on the other hand, redundancy when the spins are all in the same direction, both in the non-frustrated and in the frustrated. On the other hand, we have synergy when the spins don't have all the same sign. So basically, what determines the fact that the global O information is synergistic here and redundant here is just the number of times these individual states are visible. But if we look at the individual state, we see that we have still synergy in the non-frustrating system, sorry, redundancy in the non-frustrating system in the local case, and synergy in the frustrated system, again in the local case. As a, let's say, more fun application, of course, since Fernando was in the paper, we did this for back corrals, in which you look at the information, local information, not only between ports, but also between ports and the words. So you will find everything in the paper in terms of the time, and if I'm honest, given the extra thing, then with the proper rigor first of all, we also have some background in music theory. So this is just now we have seen factors, we have seen local measure, and now we see another expansion of this O information, which is the gradient of O information. The gradients of information are something that try to basically reconcile a parsimonious view in terms of what happens to single variables, what happens to pairs of variables, when we are still considering the higher order information. So the idea is that still look at the higher order information in the system, but we focus on what happens to the higher order information in the system when either a single variable is added to the system or pairs of variables and so on. And basically we can do this at different orders. So if we ask ourselves what is the variation of the information when a variable is added to the system, we have this first order gradient and second order gradient. Again, it's quite parsimonious, and of course we don't want to arrive too high value otherwise the feature properties in principle. And also gradients are symmetric on the permutation rings. So you don't have to care about whether you add the first one or the other. I mean, this you can, but it's a different question. We will see this later. And so again, we have two cases. Frustrated system, one with a central spin, which is synergistic, while all the others are not. And so we have the first order gradients for spin 1 and spin 7. And of course, this curve is equivalent for spin 2, 3, 4, 5, and 6 as a function of the inverse temperature. And then you have the second order gradients and the local formation, again for the curves which are not identical. The situation changes when you have this system with periodic boundary conditions in which you don't have anymore this central synergistic spins. So also here you have that depending on the temperature, the spin can be synergistic or redundant. In fMRI, we can have first order, second order, and third order gradients. Uh, Now, at the level of where the individual variables are the different resting state networks. So again, we see that for the first order, basically everything is redundant. The only one which displays some synergy is the default network, which is indeed a ubiquitous network present in the resting state analysis. So, the default network is basically sensitive to any modulation you can think of, very unspecific. And then when you go to second order gradients, you still have most redundancy. On the other hand, when you start removing redundancy and you arrive to third order gradients, there's the sandwich, you start having quite some synergies. Continue. As another newer example, we can see higher order multiple in local field potential recorded in rats, in which the different color corresponds to different functional regions of the brain. Again, redundancy here comprises electrodes which are in the same regions. On the other hand, synergy comprises electrodes from different regions. If you want to dissect a bit what is in here and here, you can look at the gradients. So comparing these figures, which are the same as before, with the gradient. So the first order gradient, all the regions are all redundant except from the hippocampus, which displays small synergy. On the other hand, when we consider groups of variables, again we see that if we take pairs of regions, or pairs of contexts with different regions in the brain, we have synergistic contributions when these two variables are added to the system. So these two are complementary ways. This one is, let's say, this one is focused on individual pairs of variables on the same, let's say, behavior, higher order behavior basis. If you don't like neural, you also have macroeconomics indicators. These are where you have again a similar thing. So the hippocampus here would be this differential of the gross product. On the other hand, the other variables are all redundant. On the other hand, when taken together, you have strong synergies coming up from different indicators of macroeconomics. Now, sorry, with all this application, because I'm selling carpets, which I am. As another example, we have another decomposition of transparency, which starts from this critique of information flow by the groups of transfer, which basically say that, okay, now we are obsessed with networks. We use transfer to construct networks, so we have three wires, and then we are assuming that everything is AI, and there is no high-level information. And so the idea is that given two items in a complex system, if we have a driver and a target, either we can do in a pairwise fashion, or we can condition to all the other drivers. Now, of course, conditioning is sort of a bad idea if you don't know how to do this properly. Because if we condition variables which share the same amount of information, we could have spurious negative correlations, etc. And so even if we could condition all the variables in the system, it would never be a good idea to do so. Or we can do this functional technique. I did. I'm sorry for that. So, or we can have indeed the functional equivalents, which are the graph circles that I showed you. Now, is there anything in the middle? So something that can sit around to focus on the driver target pairing, but considering also the rest of the system. So in particular, given a pairwise link, so if we are after a certain driver target pair, how much of it is due to the environment and how much of it is due to a pure two-body interaction between the two variables. In order to do so, we start from a property which we always have the entity of the value is greater or equal to the condition to other variables. But this doesn't hold for the mutual information. Indeed, conditioning the mutual information on the rest of the system either reduce information shared between X and Y or can increase. So in this case, you would go towards detecting redundancy, and in that case, could go on towards detecting more synergy. So the idea is to apply a sort of iterative partial conditioning, either minimizing or maximizing the mutual information between a driver and the target. So with this, we can redefine some quantities which already are familiar to us in the partial information decomposition, namely unique information, redundant information, and synergistic information. And so if we have a driver and a target, we can decompose the pure two-body effects and the effects due to the environment, which can be either synergistic or redundant, or redundant, which can be then obtained by successful decomposition of the transfer entity, either minimizing or maximizing the pairwise transfer entity. Let's see how this works in a simple case in which we want to have the transfer entity between x1 and x4. So we have the pairwise transfer entity, and then we have all the possible conditional transfer entities. So we have a pathway which maximizes the information between these two, and so this is a synergistic path. And then we have a redundant path passing through x3. And so in this case, we have some different decomposition of unique, redundant, and synergistic information. The dotted lines are the actual links, so there is no direct unique information. But you have information between the others. Sorry. Another example, we can ask how much of the transfer between any estimation are due to pure two-body effects or the time. And so we did this, of course, by checking for different surrogates. So we can see that, for example, for the pathway minimizing this line is the pairwise transfer entity. So we can either minimize it or maximize it or increase it when adding more variables. So we see that there is one variable which would minimize the pairwise transfer entity, so one redundant variable, and two variables which, on the other hand, increase the pairwise information, and so they are synergistic. And then, if we go to higher orders, this is no longer seen from the surrogates and then we stop. And so, by comparing redundant, so since the sum of redundant plus synergistic information divided by this Tm value is about 0.2, we can conclude that about 20% of information from the mean is due to many body effects, in particular due to these two indices, and the rest pure two-body the two variable effects. So this is another decomposition which starts from a variable, two variable of interest, in particular the driver and the target, and asks what the system does in shaping the interaction between these two. The same framework, identical, can be used when we have the problem of prediction in a typical regression problem. One strategy of doing multivariate modeling is the so-called leave one covariate out, in which you basically compare the error of the model containing all the variables, so the variable of interest and the rest of the system predicting the target, and a reduced model when you are removing one covariant, in particular the covariant of interest. parameters. So we can do the same, which is basically uh, minimizing or maximizing the pairwise prediction in terms of synergistic learning. So we apply simulation in which basically we simulated electron proton inelastic scattering and we want to discriminate pions and protons. So here we have the classical regression, both with the pairwise, so in which you do regression all the single parameters and the leave one covariate out. And here is our proposed modification in which we have synergistic, redundance, and unique contribution to the regression. And we can see that, for example, uh, these two energy variables, in and out, which are completely excluded in the leave one covariate out because they are redundant with respect to another variable, which is, on the other hand, important in the prediction, in this case P, still can give us some information in predicting, in our case, the discrimination between pions and protons. So this is, let's say, an approach to regression which merges the pairwise approach and the multimodal. Okay, as a final range of application, let's see what happens in the information dynamics at transition. This is a simple empirical result of a system of parameters layers undergoing explosive synchronization, and then we have the transfer entropy of the system. So when there is explosive synchronization, also transfer entropy goes up and then goes down. This is, of course, intuitive because when the system is completely chaotic, there is no exchange of information, but also when the system is completely synchronized, we don't need any more information from the drive to predict the time. So again, transfer entropy. So, of course, in easy systems, is expressed at the transition between the non-organized and organized state, so in the critical regime, and of course we can then extrapolate this to different cases in real life. So it has been shown that the pairwise and the global neutral information peak at the critical temperature. Now, these numbers are converged at this stage, just that since in our paper we work with inverse temperature, we not confuse you. I decided to do this rather than changing my fingers. On the other hand, it has been shown in a subsequent paper by Barnett et al. That not the pairwise, but the global transfer entropy peaks in a paramagnetic phase. So this is an result. You can have a warning sign for the transition from disorder to order in the paramagnetic phase. But on the other hand, this involves computing transfer entropy across the system as a whole. So we can ask ourselves, first of all, we can have the process of transition also based on static data instead of taking into account the history of the system. And then we really have to measure all the variables, or we can build precursors based on a small number of variables, even as small as 3. And so by using the partial information decomposition, both for zero lag or lagged interactions, as shown yesterday by Pedro, we have shown that it's actually the synergy that peaks in the paramagnetic phase. On the other hand, the redundancy here with the dashed line still peaks at the transition. So the synergy is responsible for the peak of the transfer entropy in the paramagnetic phase. As a further confirmation of this, if we take as a target the sample of spin 1, we have spin 2 and 3, which are very synergistic with respect to it. And so the peak is farther away from the critical point. If, on the other hand, we look at 6 and 3, which are much less synergistic, then the peak is moving towards the the critical factor. So we have seen that is the synergy that is responsible of this information of this peak in the paramagnetic phase. So this is another evidence for the fact that the higher order behaviors emerge from pairwise states. In this case, the pairwise coupling of an Ising system is, on the other hand, another example from Stephen Turner group in Vienna, in which function dynamics relevant to the higher order, which could be already explained by pairwise dyadic. On the other hand, yeah, I forgot this. With this fact, the fact that the signal peaks in a paramagnetic phase, and this is a sign of emergency, we try to investigate blocking, which is common in machine learning, when the system for a moment looks like it's not learning anything more, then all of a sudden it learns a lot. And so, by looking at the synergy and the redundancy and the unique information between different features of a learning system, we have seen that the synergy also displays a peak in the graph phase. So we can see graph in machine learning again as an emergent phase transition. Okay, all nice, but indeed, I think that the network scientists and statistical physicists still don't talk enough. Because when, for example, a simple thing like the Ising system, uh, we try to put it on a realistic network, not on a lattice, things change. Actually, I learned this the hard way. Our paper on the synergy, even before that, we were studying synergy in the connectome model, so the real world network. And then our paper went through some phases already, and then at a certain point, part of you are saying, I'm not sure if I'm going to do this anymore. And that paper was rejected. Then, more than 10 years after, when studying doing the master thesis seminars and with this result, which I will show you in a moment, I realized that the problem with Barnett was that we have shown that indeed even the payload for fact was speaking away from the paramagnetic phase in a real world network. While in his paper it was saying that it was on the low. And so that's why he was basically trying to verify these things to learn after 15 years. Anyway, indeed, if you look at Ising system on a network which is still quite unrealistic because it's a tree, but it's no longer a lattice, we see that there are some groups of variables for which the synergy peaks in the paramagnetic phase, and some group of variables for which the synergy peaks outside of the paramagnetic phase. So if you look at all the different communities, you have this mess. So on average, the synergy still peaks in one paramagnetic phase, but not for all the variables. So which triplets are most predictive of the network transition? If we talk about transition, about paramagnetic and sorry, between order and disorder. So Stein looked at the different network properties, different pairs, and he sort of finds some universality class. Basically, seeing that there was a minimal shape, in particular this star, which allowed to predict the synergy at the early phase. Here, indeed, you have many overlapping curves for different type of star-like networks. And so, indeed, since the transfer entropy curves only about the degree cares about the degree of source and the target for a tree, then we give the minimal shape to reproduce source and target with a certain limit. And the same with synergy. The shape becomes a bit more complicated. 3-star line. And for a real world network such as the karate network, we still see similar results with some topologies having synergy in a more. These results are indeed confirmed by others, started for example this one by Joe and Leonardo, which show that the network structure has an influence on the synchronization. Okay, so just to finish, do we really want to reconstruct network from observed dynamics? Again, most methods are meant to disclose the effect and not the mechanism. The effect can involve links result from trigger dynamic effect without the perfect generative model. Also, spurious link, and I put it between quotation marks because if you look at the data, who are we to say that something is true? If it is a mechanism for which those things is perfectly legit. And also, yeah, not that information just because we can, because we can. Okay, so yeah, I hope to have shown enough evidence that is good higher order interaction, but not only those, because sometimes painless interaction can be informed. And thanks to my collaborators. And since I have still 2 minutes, I will do something that Pedro was talking about yesterday. So we'll do the repellente Nino Vitente, for those you know. And I will do some very anal commentaries. One is about Venn diagrams. So Venn diagram, I also use them. Our field is unfortunately plagued by axioms. Some people like axiom more than others. And indeed, we say that okay, we cannot actually represent this with Venn diagrams because with Venn diagrams you cannot represent the negative qualities, etc. So one reviewer will not tell me how many is the bigger sense and go, okay, fair enough. There is zero practical application. But if you already want to be mathematically precise, then the frame I'm going to propose is not something pages of pages of algebra. So in the practical sense. But if you are a mathematician, maybe. Another repellente linear entity is a note of estimators. Sometimes you can use a covariance estimator, sometimes you can use opinion estimator. So you can look at multivariate information as reduction in variance or as reduction in surprise. So either you use the standard constraint or you use a covariance matrix. But if you care about the balance between synergy and redundancy, you need to take into account that is concave and to be measured stable. So if you have groups of variables for which the reduction in variance is the same, on the other hand, the reduction in entropy is not the same because the entropy is also in the same shape. So logarithms are there. Next.
Thank you very much for your talk. We have a few minutes for questions. If you have a question, raise your hands and we'll give you a microphone. Well, I have a question for you. When you are using hypergraphs, the complexity of the model increases a lot, in particular, the degree of the hyper edges. If you keep it increasing, then everything can be related. Is there like a physical constraint on how many elements can be hyper edge?
So physical, no, because this is a behavior. So in principle, everything could become significant. What we do, and only a few portion of people do it, the other doesn't give a shit, is to make sure that the higher order data is not significant only because it contains lower order. So for example, a multiplet of order 4 can be synergistic because it contains triplets which are synergistic, but not add the fourth one will not add against the information. So what we did is to compute the confidence intervals for all the lower orders and then compare it with all the possible confidence intervals of higher order. Is the pain in the ass, it makes things much stronger, but especially when you compare the physical constraint. Otherwise, everything becomes.
Yeah, computationally, if you have hyperedges with k elements, the complexity of the model can increase exponentially in the number in k. So, like in condensed matter physics, sometimes we have like power laws or exponential decay laws or some constraint on the size, like logarithmic liquid elements. You don't have something like that yet. Okay. Someone wants to ask a question. I don't see a lot here, so you have. Okay, are you category theorist? It's not category theorist.
Good answer.
Yeah, that's all. How computationally costly is it to compute methods?
It depends on the estimator that you use. So if you use a covariance estimator, then it's easier. If you use a weighting estimator, worse, but it's worth one because you generally work with a big estimator sum, big time. If you want to use a more rigorous estimator, you use a reinforced or rest estimator to estimate that. Very important to have.
I have a question, maybe again out of ignorance. So in this case, in which you have three variables, one output and two inputs, imagine that, in this case, in which you have a latent variable, for instance, or a couple of latent variables. Imagine that, yeah, the thing that you mentioned at the beginning, that you could have two latent variables, and but the overlapping of the distributions
Yeah.
was somehow related to synergy. So imagine that you want to create a classifier on a variable that you cannot observe. For instance, depression, imagine that depression, but that variable is not continuous. You don't have a spectrum of depression. Imagine that in this abstract latent world, this variable is bimodal somehow. Do these methods still apply, or are there some assumptions about these latent variables that has to be fulfilled in order to apply this
First
idea?
of all, you would not put it because in order to categorization of questions, you should look at other variables. You not just use, even if you use the minor execution, even this thing, PSM file, is about impression, but then there are already a thousand
Web, time for a few questions. Do you have any? Okay, this is your fault. Okay, like when you have graphs, you can use sparse sampling methods to reduce the size of the graph. Is there something like that hyper edges? It's your fault. You should have asked this question.
Why would you reduce it?
Like sometimes the model can be very large, too many nodes, too many edges, too many hyper edges. Sometimes, like when you have a population, you have like imperfect data reconstruction, and you only sample some points, or you resample the size of the graph.
In my opinion, if you have to do this, then you are asking the right person. If we are, I mean, even like applying something as suboptimal as correlated to the next are still, you have the responsibility of saying, okay, I'm applying correlation between me. I think there is a method behind this correlation. So I apply correlation between how much I weigh. So the number of variables you choose and the number of variables which you decide to produce statistical differences is on you. So if you say none of my graph is too big, that means reduce with some numerical things. Isn't it a process because you're not having a better process, you're just trying to fix something that you should fix.
Okay, thank you. I think that's the next question in the poster session. We don't have more questions. We can change speaker, please. Let's name a speaker again. Welcome the next speaker. Okay, our next speaker is Samuel Johnson, who's going to tell us about traffic analysis, and I'm going to read the title so you can.
Thank you very much. That forces me to read my title. But I left there even though I didn't really know what I was going to say at the time. Just by myself too. This is a bit of a random collection of slides I've got. I have to go deciding what to show you. So first of all, thank you very much. Thanks to Joaquin and to everyone else who's helping to organize this. It's really great to be back in Granada again, even for a short time. And it's making me think I should start going to more conferences again, something I haven't done for a while now. So I'm going to be talking about traffic analysis. I don't know if I can point which is a method for studying hierarchy and directionality in complex systems. Tell you what that is. But first of all, as we all know, complex systems are these systems that tend to have lots of elements that somehow interact with each other. And this makes for a nice description of the network, usually because we can say, well, the elements are the nodes, and we represent interactions with edges. Typically, we have some kind of dynamical variables that we're interested in too. Like this might be the action potentials of these neurons. The neurons form an actual physical network, but sometimes we have something like the network underlying an ecosystem that we call a food web. There's the network of interlending between banks, whatever, there are loads of networks. And of course, there are lots of different ways of trying to put more or less information in our representation of the dynamics or in the network itself. So you might say, well, I'm going to have weights on my edges to represent something. Or of course, let's have higher order interactions, things like that. But something that I think we don't usually pay enough attention to is the fact that these interactions are not usually symmetric. So the fact that A has some sort of influence on B doesn't necessarily mean that B can do the same back to A. So for instance, we have pre-synaptic neurons and post-synaptic neurons. Or in a food web, we have the predator and the prey. Interactions between people, the interactions don't always mean you can go in either direction. And if you look at the information that you've got in these directions, often you find interesting things in these systems that you lose if you decide to just look an undirected network. So this goes back a long time. By the way, I apologize to any of you who have already seen these slides, maybe several times, because I'm not very good at making new slides, so I keep using my same pictures. And I'll promise to get onto some new slides at some point and just look away at the notes. So this goes back to when I used to live in Granada, and some of us are looking at ecosystems. And a thing that ecologists tend to do is to assign to each node in their food webs what they call a trophic level. So that just means if you're a plant, then you have level 1, if you're a herbivore, level 2, a carnivore might be a level 3. Just gives an idea of that hierarchy. But the general equation would be this: the trophic level of a node I is 1 plus, this is just the average of all the trophic levels of their prey. So this is the adjacency matrix, this is the level, this is the in degree. This adjacency matrix could be weighted if you want. And you can represent this with matrices like this if you want. So you can say, if I write down this L matrix here, and this vector B, which is basically the degrees, then I can express this as this linear system of equations. I solve for S, and those are my trophic levels. But what we wanted to understand is to what extent does some kind of degree of order in the system then relate to other things that I'll get onto. And so what we did is to assign to each edge a variable x, which is the difference between the trophic level of the predator and the prey. So how far apart in some sense the two are. So like this bird's a long way away from the plants, but it's much closer to the snails. And then you look at the distribution over all edges of this variable x. And distribution might be something like that. For some reason, it usually looks like a Gaussian, but I don't really understand why. And then the standard deviation of that distribution tells us something about how well this is organized. And so this Q is basically just the standard deviation. And I'll show you why that means what I'm saying. So if you take a network like this one, we have Q equals 0. And what that means is that the nodes fall into these integer trophic levels. All the trophic differences are just 1. And if you have a bigger Q, it means it's a bit more random somehow. But still, this is still much more organized than it could be. So the average Q for this network, the expected value should be something like 2, but actually this one has a much smaller net value because there is a degree of order here. but it might not be obvious if you don't measure these things. So what we were thinking about, well, like 10 years ago, maybe more, I can't remember, was this problem of maze paradox, which in ecosystems, or maybe more generally in complex systems, was how can it be that if you try to look at the stability of a system via sort of linear stability of a fixed point, it would seem that the bigger the system and the more interconnected it is, then the more it should be unstable. Because basically all the eigenvalues get further away as you make it bigger. But that doesn't seem to correspond to reality, where we have these big ecosystems like the Amazonian rainforest that are quite stable. So if you simulate this, and I won't go into these details, but this is just the way Bob May used to measure stability in this paradigm, and you can predict how instability should increase in a random graph. As I increase the number of species in my ecosystem, it should get more unstable. And these are various different food web models. So there's the niche model and various other derivative models that ecologists use. And sure enough, they all get more unstable as you make them bigger. But if you make a model, the model that we used, which the only real thing it does is to tune the trophic coherence with this parameter t, we find that in the incoherent networks, the behavior is the same, but the more coherent you make it, the lower this slope, to the point that you can have a system like this that actually starts to become more stable with increasing number of species. And I don't know how much this analysis really corresponds to anything real, but if it's true, then it does make for some interesting possibilities. So if you live in a world like this, where a system gets more unstable as it grows, then you'd expect it to hit some kind of threshold where it just can't keep on growing, and you'll maybe start losing some species. And so if you fluctuate, you go back to the regime of stability, you get too many species, you become unstable. Maybe this is some kind of self-organized criticality or something. But if you live in a world like this one, you might be stable, but you lose some species, and that pushes you over a tipping point. And the only way to regain stability is to lose lots more species. So it would be good to know in real systems what kind of world we're in. Anyway, that's kind of the background of this. In more recent times, we've actually come up with a slightly different way of measuring trophic levels and trophic coherence, which probably is actually better for most purposes. This was an idea of my friend Robert Mackay in Warwick. And he said, well, what about instead of measuring those trophic levels and then using them to measure the coherence, we just write down an expression for the incoherence for some arbitrary trophic levels that I'm going to call H now. And then I minimize that, so I find the levels that give me the minimum incoherence. Well, actually, that's satisfyingly easy to do. You just take the derivative of this thing, equate it to 0, and you end up with an equation that looks very similar to the one I showed you before. Only now this L matrix has the in and the out degree, and it has the adjacency matrix and its transpose. You can think of this, if you like, as the Laplacian matrix associated with the sort of symmetric version of this adjacency matrix. If we ignore the x directions and took Laplacian, that's all this is. This V is the imbalance vector, the difference between the in degrees and the out degrees. So you see, it's just a matrix equation. And it's worth bearing in mind for some of the things I'll show you later, that everything can be done by just solving a linear system of equations. So sometimes it will help us to understand other things that are much more computationally difficult to get to, and this can give us lots of insights. Then once you measure these levels, then the F is the F that corresponds to those particular H's, and this F is bounded between 0 and 1. So 0 corresponds to maximum coherence, 1 corresponds to maximum incoherence, and that's our graph. So just to show you sort of what they look like a bit, these are some ecosystems. Here we have a very coherent ecosystem, a very incoherent one. This is in between. And these are the sort of standard levels of the ecologist. These are our new levels. They don't measure exactly the same thing because these ones are the ones which are sort of optimal in some sense. But they're quite similar, and the idea of coherence is still more or less the same thing. We're sort of measuring, I think, the same idea in two slightly different ways. Okay, so what exactly are we measuring then? So let me show you some different interpretations of what I've just described. So this is sort of how we see it. We think we've got this distribution of trophic differences, I call this X, and I'm interested in how broad that distribution is. In the description using Robert's levels I just showed you, it turns out that you can relate this standard deviation to f, but you can also relate the mean to f. So the mean of that x is equal z, and it's just 1 minus f. So sometimes we call that direct interval. It's like or we could also just call it tropic coherence. Basically, z is 1 when it's not incoherent, and 0 when it's very coherent. So we think about it like that. But then it turns out that these same equations have come up more times. As far as we know, at least these other 2 times. One is in Helmholtz-Hodge decomposition. I don't know if anyone has heard of this. Maybe people who do things with vectors. I haven't heard of this before, but basically you can take a vector field and you can separate it into the part that has all the gradients and the part that has no gradients, so the conservative part. And when you do that, if you do it on a network, as apparently lots of people do, well, it's useful for some purposes, and the equation for what's called the circularity, which quantifies how much of the field is in this part, is exactly the same as our f. And here's another thing that might be even more intuitive, actually, which is called spring rank. Some people invented this to try and rank like teams in sports or something. And they said, well, let's take our directed network, and we're going to put on each edge a spring. And so springs want to have their preferred length. So if you stretch them or you compress them, then because of Hooke's law, they try to go back. So you can write down a Hamiltonian for that. You can let it relax to its minimum energy state, and lo and behold, the values of the positions that the nodes adopt are the tropic levels, and the energy is our f. So there are all these interesting similarities, and maybe it's not so surprising that this equation keeps coming up, because first of all, the equation is very simple. So it's just this average over all edges of this variable that we have on each edge, x minus 1, the square there. And we might say, well, that's a bit arbitrary. What about if we replace this 1 and this 2 with some constants? How does it change things? Well, one thing it changes is that the only way you can solve this equation easily is when it's equal to 2. Because thanks to that 2, we take the derivative and we have a linear equation. Otherwise, we end up with a nonlinear equation. You can solve it in the computer, but it's not so nice. And the other thing is that this alpha really doesn't matter at all. Alpha is just like the length that the springs want to have, and so it's just, you might as well call it 1. If you give it another value, you're just rescaling things, but it's a unit, but it doesn't mean anything anyway. And we've done it for some other values of beta, and qualitatively it doesn't really change much. The ordering of the nodes and things is similar. So we stick to this equation. So why does this matter so much for complex systems? Well, one of the reasons that it crops up in lots and lots of things that we've looked at in dynamics and in topology is the effect that it has on feedback, which was already anticipated with this Helmholtz-Hodge decomposition, which I'm not going to say anymore. And so one way of showing this is to use graph ensembles. So this is an idea from statistical mechanics that you can use with networks. And you may be familiar with the configuration ensemble, which is the set of all possible networks in which we fix the constraint of the in and out degrees. But we just added another constraint, which is the tropic coherence. So if you set those constraints, and now you look for expectations and distributions over things you can measure, it turns out that we can represent a lot of things in terms of this f. For example, the expectation for the spectral radius. The spectral radius is associated with lots of processes in dynamics, related to synchronization of oscillators, for example, and absorbing times in various sorts of dynamics. And you see that the expectation for the spectral radius is this form, and this tau just depends on the in and out degrees. The L is the number of edges, and the S is the number of edges that connect to sources or sinks. So all this depends on the degree distribution, and this depends on the coherence. And the reason we can do this is that if you imagine a network, and you want to know whether a path through your network, or a walk, I should say, through your network, comes back to where it started, you can actually work this out in expectation, because you can equate that to a random walk where you're hopping up and down in tropic level state, and the size of your hops comes from your distribution, which is exactly your traffic difference distribution. And also this gets better and better for longer walks, because the central limit theorem means that all these things add up nicely. You get the Gaussian, and you can predict the probability of you getting a cycle of a particular length, given these constraints. And it works very well with real networks. So you take real networks out there, whatever they may be, language networks, trader networks, neural networks, and you look at their spectral radius and you plot it against tau, and it follows this curve very nicely. Basically, what we have is two different regimes. We have a regime where tau is positive, which is when the networks are quite incoherent. And really, this is the regime that everyone always explores when they do new fields and when they just assume that networks are sort of random, or when they ignore traffic coherence. But there's this other regime that real networks often adopt, which is called loopless. It doesn't mean it has no cycles, but the number of cycles, instead of increasing exponentially with the length of the cycle, they decrease exponentially with the length of the cycle. So you get some cycles, but they're quite small ones. And so this, you can see, will have a bigger effect on various kinds of dynamics. And a sort of similar concept is how it affects strong connectivity. So in a non-directed network, your network can be connected, or you've got more than one network, basically. But in a directed network, it's weakly connected if it's connected when you ignore the directions, and it's strongly connected if you can get from any node to any other node in the network, respecting the direction. And so typically real networks aren't ever strongly connected, but they are usually weakly connected and have a strongly connected component of nodes. And the size of that component and which nodes it is depends a lot on the traffic structure of the network. So something that we did here was that, well, we realized that the strongly connected component of real networks tends to depend on a very small fraction of nodes, of edges. And those edges, to a good approximation, are the edges whose traffic difference is negative. There's a small fraction of edges that go backwards. So for example, in this network, if we remove these two edges, there's no strongly connected component, basically. So we can again do theory to predict. It's something that Niall did, my PhD student who's now working on astrobiology in Edinburgh, but he's before that he went to do lots of interesting things on this. And he worked out a theory that predicts the number of edges that we need to remove to make it acyclic. And if you remove you take a real network, this I think is the C. elegans neural network or something like that, and if you just remove the edges randomly, your strongly connected components gradually disintegrate. But if you remove them according to trophic differences, it disintegrates much faster. I believe that to do this sort of exactly can be hard, so we can get very, very close to the best solution by just solving this linear system of equations. And another thing I won't go into here, but you can see why it would be the case, is that the amount of influence that the node has in the network, or how much it is influenced by other nodes, depends a lot on where it is in the sort of trophic structure. So you can do lots of different dynamical models have this property, but let's say Kuramoto oscillators, we've done these oscillators, like some of you guys have been talking about, and it turns out that a very small number of nodes can drive the whole system and make the whole system synchronize with their natural frequencies if you choose the nodes that have low traffic levels. And that also works in both the model and lots of other models. And so there are lots of things that we've been doing. I really need to start doing something else. These are just the things that I have been involved in and that I remember offhand. But other people, I'm glad to see, have started doing it without asking me about it now. So maybe I can do that. But there are lots of different things, sort of topological properties that we can relate to traffic coherence, like a non-normality or things to motifs. There are various different applications, for example, that people have done to things like systemic risk in the financial sector, or to how likely your train is to be delayed, but various things like that. People are using it now also for EEG networks and epilepsy. But I'm going to talk, I can't remember what comes next. Okay, this is not more relevant for this talk, because I want to show how this could really be a method to understand something about persistence. And so I think there's a lot of information to be found in the trophic levels of nodes. For ecologists, this is just obvious, that the trophic level of a node tells you the kind of creature that you're dealing with, if it's like a cabbage or a dinosaur or whatever. But people don't usually measure with other things. But take, for example, this word adjacency graph in this excellent book, In Length and Hand. It's a very quick read, and it only has 50 words in it. If you connect the words so that consecutive words have a directed edge if they appear in the same sentence. And you here, for some reason, I put them going downwards because it looks nicer like that. So you can find sentences by just following these paths. Well, if you then color in the words by the syntactic function, well, it turns out that the trophic level resolves quite well with the function in some cases. For example, there's a big difference between the trophic level of the nouns, the blue ones down here, and the verbs, the red ones up there. And that's in a network where we know the function, but maybe we can use this in networks where we don't know the function. So this is the transcription network at least. A typical way of plotting it is like that. I don't remember, or maybe I never knew, what these different colors really represent. They're different kinds of things. Maybe they're like RNA, transcription factors and genes. But they must mean something because they have these colors in the database. And when you do it by trophic level, well, it separates things out. So maybe where a gene is in this hierarchy tells you something useful. Or this other example. I don't know how many can see any of this. I'm always telling my students to make their natives bigger. So when I click their pictures and copy them, people can see. But somehow I also make my natives maybe different sometimes. So these are two different input-output networks. So those are the sorts of things that economists study. They take sectors in the economy and they look at the outputs of one industry go as inputs into another. Maybe someone makes nails and they pass them into someone else and they use the nails to make cars or something. And they use the cars then to, I don't know, drive people to school. So it's like inputs and outputs in these different sectors. And this is for the US and this is for Saudi Arabia. And it's interesting because you start to see things like at the bottom you have sectors like finance or energy that mostly input into the system, and then at the top you get things like healthcare or construction that receive inputs. But you also see some differences. For instance, education is low down in the US network, but it's high in the Saudi network. And I don't know why, but maybe it could be useful for someone to know that. Potentially it means that in the US, the education creates a lot more spin-outs and then pushes it down to the trophic level. I don't know. So there are things like this that I don't know how to interpret, but I'm looking for someone who knows how to interpret what they use. So this is a database of book translations that the UN has for some reason. And so it's lots and lots of books that have been translated. And every time there's a translation from, let's say, English to Spanish, we write an edge from English to Spanish. And in this network, you could also see some of these interesting things. You've got a big node of a lot of centrality, which is English. You've got some European languages over here, other Asian languages. And towards the bottom, you find things like Sanskrit and Old High German, things that you don't normally translate into, but you translate out of. And at the top, you have things like Esperanto and Aragonese and things like that, which you tend to only translate into. And so you can also use these to say something about the state of how alive the languages are or something. Okay, and this is about dynamics. This is a really simple example, but it's really just to illustrate why it's important for dynamics, and it's not as simple as just the picture I gave you before of May's paradox looking at linear stability or whatever. Remember that in the case of the linear stability, it seemed that trophic coherence made systems look more stable. They look like ecosystems were getting more stable thanks to trophic coherence. Yeah, it's kind of the opposite actually. So here the simplest thing you can do, I think, with the neural network of the worm C. elegans. So I took the C. elegans network with no weights, just the directions, and I put a network which you could interpret to be a Hopfield neural network with no pattern, just with one pattern. But you could also say it's just a majority rule dynamics. You've got some variables that can have -1 or 1, and they just at each time step they synchronously update, and they take the state that's the majority of the incoming inputs. Simplest thing you can think of. Of course, it does what you'd expect. The average of the nodes is either going to go towards 1 or to -1. Here it's gone towards -1 and it stays stably close to -1. But that's actually not the network of the C. elegans. This is the randomized network of the C. elegans. So I took this network, I randomized the edges, conserving the degrees, or even out degrees, and it behaves the way we would expect from our theories of new field and that sort of thing for these dynamics. If you do the actual C. elegans, you get something quite different, where they have these hops between these two bistable states. And by the way, there's no stochasticity with it. There's no temperature. Why is this thing cooking? The only stochasticity comes from the fact that if there's a tie, if it's 50-50, 50% of my input say negative, 50% say positive, then it's a coin toss. One side. That's the only time you get a random choice. And that's enough to make this interesting thing here. It turns out that the times that you stay on these metastable states depend on the tropic coherence of the network. So in a very coherent network, it just randomly jumps about. In the very incoherent network, it's stable basically, or suppose it will only be stable if it is continuing. And then for different levels of coherence, the permanence time depends on the coherence. And can we use that for something interesting? Well, this is a hot field neural network with a married this doesn't change because a married and so I don't know how familiar you are with this kind of network, but basically you can store some patterns of activity, some information. You've got 4 different patterns, which I represent with these 4 colors, and I store them in Hebbian learning. And now I show the system one of the patterns for an instant, and I just show a small subset of the neurons, like the input neurons. And ideally, the network would retrieve the pattern, so it would identify what it saw, and then it would stay there, so I would know what it saw, even if I remove the stimulus. But if you do it on a very coherent network, it doesn't work because it's quite sensitive, but then it just goes somewhere else. If you do it on an incoherent network, it doesn't work either, because it's too stable and you can't dislodge the pattern it's stuck. But if you do it on somewhere in between, you change the coherence, you find a regime where it does the task very nicely. It always responds and goes to the pattern it saw, and then it keeps it until you show it a new pattern. So it's for this simple task, perfect coherence. And in fact, we're using this to try and make some kind of neural network, which is something in between the standard feed-forward neural networks that people use a lot in AI these days, the deep learning type neural networks, and the recurrent neural networks that are useful for some other things to be defined for memory. Well, what we'd like to do is build a neural network that has another hyperparameter, which is the tropic coherence you can affect where you are. And in fact, the Chinese group has done something a bit like this, but not quite, because they don't have cycles. And so we expect that there might be a sort of Goldilocks zone, which is not too coherent, not too incoherent, where things moving up. By the way, the human brain and animal brain seem to have a coherence that's in between, so it should be there or something. Okay, so I'm going to mention a particular application that we're working on, which is to do, like some people talked about before here, functional or let's say neuroimaging networks. And in particular, this is to do with an experiment that was done recently in London, where they wanted to try and work out something about the mechanism of action of different drugs on depression. And so they took some people with depression, and they gave them 1 or 2 drugs. Either you can have a standard antidepressant, which is a citalopram, whose mechanism of action we don't really understand very well. People used to think it's because of the serotonin, but actually it's probably not. So it might just be placebo actually. And the other one is psilocybin, which is the magic component of magic mushrooms. And so they also did fMRI scans on these participants to see how, and we want to see how their brain changed. So the idea of Gustavo Leco and this work. Now, I'm not going to tell you about the details, mainly because I don't really know the details. I'm still trying to understand a lot of this. And also my participation is very, very minor. But this is an idea that Gustavo and people in Barcelona have been working on for a while, I think, to extract these weighted directed networks from fMRI. Well, sorry, not just from fMRI. By combining fMRI and structural connectivity information that they have, they can extract some directed networks which seem to mean something. Because in general, it's difficult to get a direction in fMRI that means something. But this, I think, explains the drug trial and the 2 different arms of treatment. This is an explanation somehow of the tropic coherence and stuff, which here we call directed gas. This is how they combine these 2, the functional connectivity, the structural connectivity, and they come up with a kind of effective connectivity, which is the data that we then analyze. And the idea is to try and say something about what's changing in the different brains when they take one or other drug, and can we see it in the tropic level, the coherence, this kind of thing. Well, this is maybe the most immediate thing we see. If we take all the patients who took psilocybin and we look at their tropic coherence and before and after the drug, and here the ones who take the escitalopram before and after the drug, the ones with the magic mushrooms tend to get more incoherent, whereas the ones with the antidepressants get more coherent. And it does resolve it fairly well. You could do like a machine learning thing, which I think is a support vector machine in this case, to classify, for instance, which drug they receive or something like that. And we can also look at the different regions of the brain and see how the different tropic levels are changing with different drugs in these regions. And this, I think, is quite interesting. If you take in this case, I think this only works for the psilocybin actually. Here what they do is they classify which drug they take, and you can resolve quite well if you took the magic mushrooms or the antidepressant. But also, it seems to be able to tell the difference between the patients who responded to one of the drugs and the people who didn't respond to one of the drugs, in the sense that they got better from depression or they didn't. So this is starting to see something about the mechanism of action, we think, that's leading to the sort of the change in outcomes that we care about. And then this is ongoing stuff that we're just doing. This is something I did quite recently where I just basically thought, well, you've probably heard about this before in other talks, or maybe you just know anyway. There's, in the brain, there are these sub-networks that people have identified already. So there's the default mode network that someone mentioned recently. There's the parts of the network that correspond more to the visual cortex or whatever. So people just know where those bits are, and there are subcortical things like amygdala and hippocampus and things like that. So I just smudged together lots of different networks, separated the nodes according to whether they were in which part of the brain they were, and then plotted the tropic levels versus the amount of connections that stay within those subnetworks. So like the different thinking about community structures, like the sort of ages to stay within the communities, and then see how the networks change when you give them psilocybin, and how they change when you give them escitalopram. And one of the changes is in the tropic levels, and you can see things like the amygdala and the hippocampus getting more squeezed down here. Here you can see them, whatever these are, getting further apart. But you can also see some changes in these connection strengths. So this is kind of what I mean by tropic analysis. It's not a properly developed tool yet, but you can invent things that you can do, and they look like they give you some information, so then you see where it leads you. And so in this particular case, what I think is happening, or one of the things that are happening, is that the connection strengths within the subnetworks and between the subnetworks change depending on which drug you take. So if you take the magic mushrooms, this is quite intuitive. If you take the magic mushrooms, the connections that are within the subnetworks get weaker, but the connections to other parts of the brain get stronger. So everything's a bit more fine. If you take the antidepressant, it does the exact opposite. For some reason, it focuses the connections within the subnetwork. And this is something I won't go into, but my colleague Catherine Drysdale does a lot of things with non-normality and pseudo-spectrum. So we're associating the pseudo-spectrum and the levels of things. So this is ongoing work also with Gustavo Deco and Ana Garcia Royo in Barcelona at their years in the brain. Now, a couple of other things, something actually Gustavo asked me. So what do we do when we have to find the networks? So because that happens quite a lot. We've got positive weights and negative weights. And at the moment, there isn't really a very satisfying way of including that in our equations. If you just include them without doing anything, you can have weird CBRs and things that work. One thing is just to take the absolute value, of course, but then you're ignoring the difference between the two kinds of interaction. Or you can just say, well, a negative interaction that way is like a positive interaction that way. But that also, in some situations, it makes sense, but usually it doesn't. So what I thought is, maybe we should do something a bit more like people do with multiplex networks, or multi-layer networks. Just separate out the network of the positive things and the one of the negative things. And thinking about those springs again, we'll have springs on both the positive and the negative links. So we've got like two layers, both of them springs. But we'll also put some springs on the connections between the layers, like weak little springs, and their preferred length is 0. So they will try to have the same level as possible. And so if you now write down a Hamiltonian for that, and we have a parameter which tells us how much weight should we give to these little intermediate springs, well, we can solve things like, I don't know why this is so fuzzy, sorry about that. I'll have to tell you what it looks like if you can't see it.
Oh, it's fuzzy.
So this is something that an inside student of mine Lucy Dumont did recently. He got hold of this network that you can't see which is a network of monks in a monastery somewhere in England. And apparently they asked them two questions, one about who their friends were, but they must have asked them also who their enemies were, because some of the interactions are positive and some of them are negative friendships, negative and positive friendships. And they also asked them who influences them, like who has a positive influence on them and who has a negative influence on conduct within this monastery. And so these monks each report some things, and then you can plot the positive weights versus the negative, the positive profit levels versus the negative profit levels. And then you can say, oh, this guy up here has a lot of positive friends and lots of negative friends. But this one down here has, for example, lots of negative friends but no positive friends, or vice versa. You can sort of see what's happening there. Or there are people who have, only negative effects or only positive effects, or both. So using this, we can maybe get to some of those sorts of phenomena. So I think I'm not finding it. I'm just going to mention these things are very interesting for having conversations with students. So this is something I also did recently, and it's all very preliminary. Don't look at the equations actually. It's not too confusing, and I don't know what any of these things are. So this is what ecologists call a consumer resource model, and it's basically like an extension of lots of Volterra equations, but they try to be more realistic in lots of ways. So they include all kinds of different things. So this is the biomass of a species, and they evolve according to these equations, which have lots of parameters and things, as well as the adjacency matrix and other things in there. And this is what's called the functional response. And it has things like allometric scaling, that depends on the trophic levels, and various different things like that. I just took that paper and plugged in all the same parameters as they use, see what you get. And so what these people tend to want to do in these papers is to see what kinds of properties are going to make the ecosystem more stable or less stable when I run this dynamics on the network. And they have a threshold, so that if the biomass goes below a threshold, then the species goes extinct and we take it out of the network. And then they look at the total biomass and the number of species. But I noticed once that this is a bit of a small threshold on this spreadsheet, because that means that whatever this may measure, if that corresponds to one creature, or two creatures even, well, imagine the full, like when B equals 1, you've got 10 to the 30 creatures, but I don't think you even have that many bacteria in the world or the universe or something. So it seems a bit of a weird thing to do. And when I asked one of these authors, I think it was one of them, I don't want to malign them, maybe it was someone else, I asked the biologist about it, and they said, well, it's because otherwise everything is just So basically this whole method is a bit bizarre. But I did a couple of changes to this. One was that I included some noise, just to make it more interesting. And the other is that I did it on a network that grows as we go along. Like look at that, there you have. So we said I just used a model that's similar to the one I showed you before. I grow the ecosystem. So every few time steps I throw in a new species, it chooses some prey and some predators, and maybe it goes extinct, maybe it sticks. When you do it like this, they often stick, and you can grow the network and make it big. And you can use an extinction parameter that's much more reasonable and still most of them the same. So it's all comes to the fact that it grows sort of organically. So this is the kind of thing you get. So in the time series, some species like the blue up this red will just stay down there. Some of them sort of go wild like this blue one, but then eventually they settle down. Some like this green one appears, but after a bit it will make it. And so you can now look at the sort of network that emerged from this. Of course, I also have a parameter that allows you to make these networks more or less tropically coherent if I want to. So first of all, if I look at the incoherence of the networks that I get, and I put in a total number of species, like I build it up to 100 species, and then I see what the network looks like. Well, when the noise is low, then you basically get the trophic coherence that you're trying to set with your parameter. But as you make it more noisy, it's more difficult to stick in the system, more of them go extinct, and so it starts becoming more coherent. So even these ones, where I'm setting a high incoherence, they start becoming more coherent for some reason. Like only the ones with the coherence survive, which was a bit too close before we get up to that. About maybe some interactions survive with specifically, if not the species for extinct. But I can also look at the expectation using these ensembles. I can look at the expectation for that value, and that also goes down, which means that some of these, like the degree sequences and things, are changing a bit too, in such a way that they're making it more coherent. But it doesn't explain all of the systems. This is a bit of a counterintuitive thing. If you look at the total biomass, which is the thing that the ecologists tend to look at to say, oh, this ecosystem is doing well, it increases with noise. So with the more noise, even though more species are going extinct, at the end of the day, when you get to like 100 species, you've got more biomass when you make it more noisy. And what I think is actually going on is that when you have more noise, the mountain of propaganda is washed down. So in a less noisy environment, you might get some very long chains, like you get in the sea, where you have like 8 different species eating each other in a long chain. But in some ecosystems, especially more terrestrial ecosystems, you have like 3 levels, and that's what all you get. And so that seems to be what the noise is doing. Anyway, so the noise somehow tunes this topology. Okay, now something that has nothing to do with tropic coherence, but I just wanted to throw it in because the tropic coherence is sufficiently controversial. I do also have some slides on climate change, which is also controversial, but I haven't shown. I'm not going to show you those ones because I haven't been briefing yet. But I can show you this, which is my thoughts on the pandemic that you might remember from the COVID-19 pandemic. So just to quickly summarize this is more or less what we were doing the way we saw it in England at this time, but I suppose the experience was somewhat similar in other places. So if you remember, the pandemic came along, people were doing modeling and things to decide what should we do about this pandemic. And at the time, right at the beginning, like in April, in some countries were starting to introduce lockdown measures and that kind of thing. In England, they didn't want to at first. And the people who I know who were advising the government at that time on this stuff with epidemiology were all saying it's good that they're not doing anything rash because there's no point in doing lockdowns and things like that. It's good that the government's following our advice. But then something clicked, and as far as I can tell, what clicked is that this chap, Ferguson, that came out with a press conference, which was very alarming, and the government in Britain immediately changed the laws, and he made some predictions using a very, very complicated epidemic model that no one can understand, about what was going to happen. And basically said that in the unlikely absence of any control measures or spontaneous changes in individual behavior, we would expect a peak in mortality, daily deaths, to occur after approximately 3 months. In such scenarios, given an estimated R0 of 2.4, we predict 81% of the British and US populations would be infected over the course of the epidemic. But then they said, well, this is how many people are going to die, depending on what we do. This is the maximum capacity of the hospital in England, which is like an epsilon, we're going to super overwhelm the capacity, whatever we do, but we should try and reduce it. And so then the government introduced a lockdown, and then it came down much more quickly. And we all thought, well, thank you for the lockdown. But this is something I did kind of not very long after this happened, which is to see where people were dying in different parts of the country. And so in England, you can get this information from different regions, and there's an interesting thing. At first, well, tragic also for other people that still seeing look at these curves. This is the number of people dying in London, and it started to go down at some point, and it got overtaken by other parts of the country. And then other parts of the country took each other. There's a kind of wave that went out from London to other parts of the country. And if you do this in a very simple SIR model, that doesn't really make any sense. If both of these curves are going up, and now we introduce a lockdown, we introduce it now, so it starts going down, there's no reason why this red one will never overtake the blue one. The only way the red one can overtake the blue one is if the lockdown comes to base, because that's when it was already going down. So, what do I think might be the explanation for why the models predicted something that was very different to what we actually saw? So I should say there's quite a lot of other evidence has come out that suggests that the lockdown didn't stop at least that first wave. That first wave started to go down first, and then the lockdown kicked in. But why? How could that be? Well, let's do a very simple FIR model on 3 different kinds of networks. Well, sorry, 2 different kinds of networks. This one is a random graph with a beta parameter that corresponds to R naught of 2.4. This is what you see happening. Exactly the same as what Ferguson and people created. Sorry, this is the random graph. They basically do the same as what Ferguson and people do because they use an assumption called random mixing, which is that they assume that everyone is just in contact with everyone else in the field. With some abstract, if you're a health worker or whatever, but there's no network. And so, yes, sure enough, it grows like this, it comes down again, the total number of people hits like 80-something% of people with autism disease. This is what happens on a scale-free network with the same mean degree. It grows much faster, and then it comes down also faster, and it infects a little bit less people. And the epidemiologists know this, but yeah, there's some differences in the network, but we can't really model a network of millions of people, so it's good enough. But this is the thing that I think they're missing, and they're still missing to this day, by the correct. If we, when the scientists estimate their R naught, they do it by looking at this curve. And so they do something like this. They assume that this is growing exponentially at first, and they infer the R naught from the equation. The same equation that corresponds to their model. And so imagine you're living in a world like the red curve here, which is a scale-free network world, where the infection rate is much lower. But at first, it grows just as fast as this curve, because of the boosting effectiveness of the network. By the way, this would correspond to what we actually see, which is that we have super spreading events. So some people infect hundreds of people. That means that if your R is 2.4 and some people are infected 200 people, then there are lots of people who are probably infected with 0 people or 1 person. It's a very heterogeneous distribution. And so if you could be a scientist living in the red world, predict the blue curve, make everyone do a lockdown, then you see that it comes down, the lockdown taker. And in fact, they kept doing it in England. Every few months they would do another lockdown, and everyone thought we were saved by the lockdown. Until the last one. The last one that was going to come along, the scientists said millions of people are going to catch it, the hospitals will be overwhelmed, lots of people are going to die if we don't do a lockdown. And the government then said, well, screw it, I won't do a lockdown. I'm going to do it. Exactly as before, it went everything down. So I think what's going on is something to do with the network. If you use this model to compare the number of people who become infected compared to the estimated R0, well, in a random world, the estimated R0 matters a lot. If you're a little bit above 1, everyone infected. But in a more scale-free world, even a very high R0, estimated R0, doesn't lead to so many people infected. Okay, last thing. The last thing is just that this idea of having a scale-free network also predicts that you get lots of waves. So you can get a wave, but most people haven't put it yet. So if now you see the epidemic again, you get another wave and so forth, like we saw in reality. With the random model, you only get one wave and you never see any more. In fact, even if you increase the infectivity, still you don't get any more waves with the random graph, but you do with the scale-free network. So this is another thing that corresponds more to that view of the world. You can see the conclusions are just that directionality matters a lot. There are many topological properties and dynamical properties that we can relate to traffic coherence. I think traffic analysis, whatever that is, can be useful to find things in complex systems. I'm happy to talk to people about it if they have anything in particular they want to do. There are lots of open questions. So, for example, I'm writing a grant at the moment. Actually, ChatGPT has already basically written the grant proposal for me, but I feel bad about using that one, so I think I'll try and rewrite it. And it's about higher order direct networks. How can we extend these things? And that's all. Thank you very much.
Thank you very much. We have a few questions.
Thank you so much. So I have a question about this trophic networks and this calculation involving a linear system. So imagine that you don't have a full sample of all the species in an ecosystem because you know how ecologies work, and sometimes it's hard to see all the species and all that. So that means that the abundances of some of the species are smaller than you think, maybe you have a lot of species with just one individual in that category because you just have seen one and so on. So how robust is this estimation of the trophic network and so on when you think that you are close but not have the full sample of the species?
Yeah, absolutely. It could be quite a useful thing to be able to do in systems like that where you're able to pass information. In fact, one of the things that we did in that paper called How Directed is a Directed Network. So I've got to go back lots of slides, but it's where I got some of these pictures from. Was actually that we went seeing how this is one I think that Basil did, where he went basically removing nodes and removing edges to see how much does that affect where the trophic levels. And it actually is quite robust. So it's you can basically estimate the trophic levels quite well with I can't remember exactly, but a surprising number of missing edges or missing nodes. And also you can estimate the local sort of relative positions quite well locally. So if you just have a little bit of local network already, you can work out these are found quite robustly.
And have you ever, let's say, visualized these networks versus measures of diversity, symptoms diversity, things like that, that could inform you how close or how far are you from this, let's say, steady state or stabilized ecosystem? I say this because in the immune system, I've been doing some analysis on diversity of the immune system, and sometimes you see one of the phenotypes just one. So you are suspicious that if you see many ones in single dots, what they call it, maybe you are under something. So there are some techniques to the extrapolation, but also rarification. And I think you've done this rarification thing with Pablo stuff and significant. I was curious about.
Yeah,
So
no,
it's another
a good idea though. I've never tried to look at data for diversity in a real ecosystem.
Okay, we could talk about this about the immune system. I think there's a huge gap there.
Yeah.
Thank you.
Okay, thank you. Very nice talk. I was wondering actually about something somewhat related. So I think some slides forward, you present something on strong connectivity or something like that, and so basically here you are doing a kind of targeted removal of edges. Yeah, is that and so the trophic one is based on some properties of the network, and I'm wondering whether because there are some algorithms to find the optimal, I mean like destroy the most by removing the least of the edges. Yeah. So for instance, so there are several, and have you compared to this kind of, and of course it's an NP problem, and it's very difficult, but have you compared to that and see how close this kind of trophic thing is?
Yeah, not very systematically, but I think I looked it up a bit and it was quite close. In fact, this is really I think for practical purposes, at least in the smallish networks we've looked at, it is a very good approximation. I actually, for a while, I was excited. I thought I'd proved NP equals P because I thought, actually, if you just remove the ones that go backwards, well, that's not enough because if I remove just one edge, the network will now change. But for a little while, I thought I had a proof that if I keep recalculating the levels, I can actually do it optimally like that. But then I proved to myself that actually not. So
No, unfortunately, it's not so easy, I think. But
it's
anyway,
a good approximation, I think.
yeah. Okay, we can talk.
Okay, I have a question, but I think I'm gonna ask it in the first session because it's very weird. It's about computation, and I think I want to close the session.
Okay.
Thank you again for the great talk, and remind people that after this we have a post session. Please do not escape, or we will hunt you. Thank you very much. Let's send the speaker.
Thanks.
Do not forget to send the PDFs to the organizers or to Joaquin of your talks, please. Thank you very much. You can also send PDFs of posters. What? The poster section is downstairs. ¿Cuántos pisos? 2 floors? 1 floor? Where the coffee break was. Let's go there. Thank you.